Hi all, welcome to our next video of machine learning. In this video, we are going to see the basics of logistic regression. Okay, so logistic regression comes under classification algorithm. So we have already seen that is machine learning algorithms. They are actually divided into supervised learning algorithms and unsupervised algorithms, supervised learning and unsupervised learning algorithms. And the supervised learning algorithms, they are of two types: regression and classification. So this basics we have already seen in the previous sessions. So regression, actually what it means, that is the predicted variable is continuous. The output variable or the predicted variable is continuous, and here in this predicted variable is discrete or categorical. Okay, discrete variable, or we can call it as categorical variable. And unsupervised learning, that is of clustering, that we can see in detail in the coming sessions. Clustering, principal component analysis, PCA, all those comes under unsupervised learning. And regression, we have seen an example, one algorithm of regression, linear regression, we have already seen. This is an example algorithm that comes under the supervised learning regression. Here we have already seen house price prediction using linear regression, that we have already seen. And the classification algorithm, one important algorithm that we are going to see now, is the logistic regression. Okay, so logistic regression, that comes under the under classification, under supervised learning in machine learning algorithms. So as we have already discussed, logistic regression is for categorical variables. So we can get into more detail. So logistic regression, that is the output y, the predicted value y, that is categorical variable. Categorical variable actually means the output variable, it's a category, that is it can be either yes or no. The output can be yes or no. Or another example, we can say in the case of stock market, whether we have to buy a share, sell a share, or just hold it. We can have three different categories in this, but normally logistic regression is used for binary prediction. Normally logistic regression we use for binary prediction. Okay, so example, we can say loan default. Loan default is an example of example case. We can apply the logistic regression, that is the loan, whether the y can be what here loan default occurs, that is the person is not able to repay the loan is defaulted, that is 1, or loan is not defaulted, that is 0. And then next example is disease detection. A particular disease, a major disease is detected, so the y is disease is there, disease is present for that person, or disease is not there, that is 0. So these are example cases where we can apply logistic regression. So we can see an example. Example case, we can say we are taking a disease. We are going to detect, that means we are just going to explain disease detection. So in disease detection, we can say y, whether the disease is present or not. Y, it can be a function of, as we have already seen, it can be a function of many independent variables. So you can say the weight of the person, for example, we can say the body weight, the blood pressure, the RBC count, the sugar, insulin or blood sugar levels, all those things. We can say it's a function of so many independent variables. So this y, it can be yes or no, that is whether a disease is present. Disease is present means actually our output, our interest, output of interest, that is actually 1, whether it is present or not. Yes, the disease is there, that indicates a 1, it's having a disease. So in the next case, it's not having, the person is not having a disease, that is 0. Okay, so actually this is the good condition, 0 is the good condition, and this is the bad condition. It's having a disease, that is the bad condition. Okay, so in this case we can apply logistic regression to check whether a person having a disease or not based on different independent variables. Okay, so why we cannot apply linear regression here? So we can just check why not linear regression in this case. That's what we are going to see now. We have already seen what is linear regression, that we have already seen in detail. Why not be linear regression? So we have already seen linear regression that the house price prediction we have already seen. This is the price of the house. This is the, if you are taking one independent variable, area of the house or the size of the house, and the house prediction we have seen some scattered variables, and through this we have drawn a line of best fit. Line of best fit we have drawn, and we have calculated all those errors, all those things we have already seen. But here if you are trying to draw, we can say we have so many factors. We have so many x1, x2, x3. All these factors are, we have different values for that, and we have our y. We already have our y predicted. So this y predicted, depending on all these values, the y predicted can be either 0. The person is not having disease, or the person is having disease. The y predicted can be like this only. Okay. The actual y value and the y predicted can be either 0 or 1. So if you see here, if you are taking an example with a simple single regression, that is the output y is a function of only a particular variable. We can say the blood sugar, so the BP of the person, and the disease is present, yes or no. Y value, here we are predicting the y value, yes or no. It can take, you can see it can take only either 0 or 1. So there are few persons with say BP but there is disease. There are another few persons with no BP but disease, like that. It can vary, actually it can vary from person to person, but this output can take only 2 values. So what will happen if we apply linear regression here? When you try to apply, and suppose we are getting a straight line like this. Okay. So straight line like this, this is 0 and this is 1. These are the only 2 values the output can take. And if you apply linear regression, we got a line. And if we want to predict whether a person having this BP is having a disease or not. So we are predicting it. We are predicting a value, and that predicted value will be here. Predicted value will be here. So its numerical value is approximately 1.5. So the y predicted, that is 1.5. That is outside our range. We don't know what to do with this 1.5. Whether it's having a disease or not having a disease, that we cannot predict from our, that we can't predict this. So we can't conclude whether this person is having a disease or not having a disease. So what is the problem is that in linear regression, we can summarize like this. In linear regression, the y that belong to all real numbers, that means the y can vary from negative infinity to positive infinity. But in the case of logistic regression, what's happening, y belongs to only 2 values, either 0 or 1 in this particular case. So this line of best fit does not make any sense in the case of logistic regression. Okay, it's clear. That is, in logistic regression, the line of best fit doesn't make any sense because it's not, the output is not continuous. The output can take only 2 values. It should be either 0 or it should be either 1. Okay, so that's why linear regression fails in this case, and we are applying logistic regression for classification. Okay, so now we can see the detailed equations of logistic regression. So as we have already seen, the linear regression is not useful when the output is 1 or 0. So it's not useful. In which case it's not useful? When the output is 1 or 0. So that is the classification case. That is, the line of best fit doesn't make sense here. So actually the y predicted, in the case of linear regression, the y predicted is given by beta naught. These equations we have already seen in the previous case, beta 1 x1 plus beta 2 x2, like that. And this is continuous. Okay, this value is continuous, and its value ranges from negative infinity to positive infinity. So from this linear regression, statisticians have modeled the logistic regression by applying a function to this linear regression equations. So that is, we have applied a function applied a function to this linear regression. So g of linear regression, applied a function to linear regression model, so that the output lies between 0 and 1. So that our output lies between, the output is not continuous, it's not ranging from negative to positive infinity, it's lying between 0 and 1. And this function is called logistic response function. This function is known as logistic response function. Okay, so we can write that function. The logistic response function we are obtaining by applying a function to the linear regression equation, so that the output lies between 0 and 1 instead of negative to positive infinity. And that function is known as logistic response function. And that function, that is actually a probability function. The probability function, that is the probability of y is equal to 1, that is the predicted value is equal to 1, that is given by 1 over 1 plus e to the power of negative linear regression equation. Okay. So this equation is actually easy, not so difficult. E to the power of negative linear regression equation. So we can say, what is the maximum value of linear regression equation? Maximum value of linear regression function, that is positive infinity, and the minimum value is negative infinity. So if we plug in maximum value here, the maximum value if we plug in, what we are getting is 1 over 1 plus e to the power negative infinity, which is equal to 1 over 1, this is equal to 1. And the minimum value we are getting is 1 over 1 plus e to the power positive infinity. So it's 1 over infinity, which is equal to 0. So that is the maximum value of this probability function is 1 and the minimum value is 0. So this probability function, probability of y is equal to 1. This is the probability. Actually, what is probability of y is equal to 1? This is the probability that our predicted value belong to class 1. So it lies between 0 and 1. So it says that our predicted value, the predicted value of an output that belongs to class 1. The probability that the predicted value of output belongs to class 1. Okay. Probability of the observation, that is to be in class 1. And if we draw this function, we can say this function takes the shape of a sigmoid curve. That is, we can draw it here. So this function actually takes the shape of a sigmoid curve. So here the maximum value is 1, the minimum value is 0. And here we can mark 0.5. This is the probability. That is, if the probability is, we can fix a line, that is 0.5 or 0.6 or 0.10, that is 10%, 50% or 60%, depending on the scenario, and we can fix it. And we can say above, if the probability value is above 0.5, we can say it belongs to class 1. And if the probability value is less than 0.5, we can say that belongs to class 0. Whether it is 0.5 or 0.6, we have to fix. That depends on the scenario. That depends on the business condition actually. So the probability of y is equal to 1. So how will you find out the probability of an observation belonging to class 0? That is given by 1 minus probability of the observation to be in class 1, because the total probability is 1. So the other probability we can get by 1 minus probability of being in class 1. Okay. So the value we get, using that we can check whether our observation belongs to class 1 or to class 0. So these are the basics of logistic regression. We can see the evaluation parameters and coding in the coming sessions. Okay. Thank you.